Last time we defined second quantized representation for two particle interactions, and then we will use that second quantized forms of the two particle interaction in the actual calculation, for example, the Coulomb energy between two electrons. But before we do that, let's switch a little bit the topic to introducing the second quantization for bosons. And we will consider a bosonic system later when we discuss the phonons or magnons and so on. But let me just define, since we have defined the fermionic second quantized fields, so it's good to just follow up and introduce the second quantization for bosons. We know that many body wave function for bosons, when we exchange any two bosonic wave functions, and the total wave function remain the same, namely they have symmetric properties under exchange, and that is fundamentally different from fermionic system where we have a Pauli principle and the occupation basis just 0, 1 for fermions, but for bosons it could be 0, 1, 2 until infinity. So let's just define that. So first let me just repeat this occupation number basis for you, and the occupation number operator acting on this states in this occupation number basis leads to the eigenvalue, which is nothing but the occupation multiplied with the state itself. And so this n varying hat nu j count the particle number when you do such an operation. So this n nu j is actually 0 or 1 for fermions, but it could be any integers up to infinity for bosons. So we could use the cartoon picture to illustrate the difference between fermions and bosons. So for fermions, as we mentioned, there are only two occupations available, which is empty or singly occupied, right? Okay, so there's no, doubly occupied or triply occupied states for fermions. And then we could go from the second floor to first floor by this destruction operator, and we could go from the first floor to second floor by creating a particle, a fermion, right? That's what we have discussed. And we cannot go to the basement because there's no basement, and there's no third floor, okay, above the second floor. But for bosons, we have infinite number of possible occupations. So this is illustrated in this cartoon picture, that we may have the empty states, or a single boson state, or two boson states, or whatever boson number states, could be infinity. And of course there's no basement, but there is no ceiling up there, so the boson number could extend to infinity. Again, we will define the creation and destruction operator for bosons, which takes you from the ground floor to the second floor by creating a boson, and so on and so forth. And you could also destroy the boson, and you could go down floor by one, and you could keep going down until you hit the empty state. So this is the Hilbert space of bosons, and we will define that in just a moment. Let's just start to introduce this bosonic operator. So creation operator B dagger for this the state nu j acting on this many-body wave function, where we have different occupations in different bosonic states, single particle states. And we know that this operation will lead to the states where there's one particle more in this new J state, and all the other states, single particle state, remain the same. Okay, so this is the consequence when we increase the particle number for new J state by 1. And then the final state is that this NUJ becomes NUJ plus 1 with a proper coefficient. So this coefficient turns out to be non-trivial for bosons. And we'll determine this B plus or B minus here. Okay, so likewise, we could define the destruction of a boson, on mu J states, and we have a different prefactor B minus associated with that operation. And we need to determine what this B plus and B minus are. So that's just a simple extension of our fermionic creation destruction operators in the boson system. So since the bosons are symmetric in the single particle state under exchange, symmetric in the single particle state, index nu J, and we must demand that B dagger nu J and B dagger nu K commute. So remember, as we defined in the fermionic case, that if I use this creation operator, C dagger or B dagger, acting on the empty states, what I mean is that I create a single boson state or a single fermion state. And in first quantization or Schrödinger picture, this is simply referring to the case that we have a single boson wave function there or a single fermion wave function there, right? So suppose I create the two bosons by, B dagger nu J and B dagger nu K, and as a result, my, space contains two bosonic particles, J and K, and with a wave function, phi J and phi K, right? Okay, and then I could exchange these two wave functions, and I get the same wave functions because they are symmetric under exchange. And if I do so, we should obey the symmetric properties of two boson wave functions. As a result, these two operators should commute, meaning if I exchange the order of these two creation operators, I will get the same results, right? So if I consider this product as just some quantum mechanical operator consisting of two operators, and if I switch these two and acting on any arbitrary quantum states or empty states, I'll get the same results. Okay, so this tells us that I first create a boson in state K, which I called psi K as their wave function, and then later I create another psi nu J or psi J. And on the right-hand side of the equation, I get the opposite order when we create these two boson wave functions. I first create, say, psi J and then psi K. So this relation simply tells us that, in Schrödinger picture, psi J times psi K is the same as psi K times psi J if they are bosons, right? So if they are bosons, as a result, since they satisfy this, symmetric properties on the exchange, and if we defined their creation operators, they must satisfy this relation. And then so if I simply just rewrite this in terms of a commutator, and they should commute. So this is a fundamental relation between bosonic operators, that they satisfy the so-called commutation relations. And this is just one set of the commutation relations for bosons. There's another one with a destruction operator. It's the same. So you can use the same argument that, suppose I have a single boson state and I destroy this. So you get conjugate wave function of this sort, and you exchange these two, and you get the same result. Therefore, two destruction operators of bosons, they also commute. But these are just trivial relations, commutation relations of bosons, and the highly non-trivial one is this. One destruction and 1 creation operator. So we will see in just a moment that this is 1, or unit matrix, unit operator, okay, for free bosons, for any bosons. But to do so, we need to fix, again, this B plus and B minus coefficient. And let's do it. So we started from nothing, from empty state, and we started to create a 1 boson, and to fix this prefactor B plus and minus as function of this occupation. So this depends on occupation. So we start from 0 particle state, and we start to build up this many boson states, and we evaluate this B plus and B minus and take advantage of such a commutation relation. So that's the strategy that we should do. Okay, so let's take a short break. When we come back, we will start to evaluate this B plus and B minus coefficients. So we start from the empty states, and we start to add 1 boson in that empty states or vacuum, or destroy a single boson from this empty states or vacuum. And because this is the, say, the ground state or empty state or vacuum, and we cannot destroy the boson if we are already in this empty state or this vacuum state. And therefore, this operation vanishes. As a result, this B minus, when this total particle number is 0, is actually 0. Right? So we found 1 coefficient, which is trivial, which is 0. And we can also require the coefficient to create a single boson out of the vacuum to be 1. Okay, so we could require, of course, this prefactor B plus 0 being 1 is not the only option we can take, but just for our convenience, we can just call this coefficient 1, and we can continue our construction. And of course, this can be any other value you like, but it can only complicate situations. Okay, so for simplicity, we just call this B plus 0, 1. So let's just try using these 2 B coefficients in this slightly non-trivial matrix element, where you sandwich this B dagger operator by the single boson broad state and the vacuum cat state, right? So this will give you some number, because B dagger acting on empty state gives you, say, single occupied state, and this single occupied state, is the same as that. And if you make a dot product, you get some number, right? Normalized. So this is non-zero. We know that. But what is this? Well, this is this conjugate of this matrix element. So this matrix element is actually the complex conjugate of this in quantum mechanics. If you switch in between, say, broad and cat states, and also you take the Hermitian conjugate of this operator, so the dagger becomes non-dagger, and so you need to take the complex conjugate of everything, and this should be the same as that, right? But we can take advantage of this definition to destroy the boson state, and this is what? This is 0 and 0 and B, say, minus 1. But this is nothing but 1, because if you use this definition, requirement of the B plus 0 is actually 1, so this is nothing but 1. So on the left-hand side, this is the inner product between 1, say 1 and 1, stay 1, multiplied by B plus 0, which is 1, and this is 1, because 1, 1 dot inner product is actually normalized to 1. And on the right-hand side, you get 0, 0 inner product, which is also 1, but times B minus coefficient in the presence of a single boson state. And therefore, B minus 1 is actually 1. You simply just compare these two, and you get B minus 1 is 1. and b plus 0 is 1, and b minus 0 is 0. So we get almost everything we need, and we can simply just, build up our many boson state based on these three coefficients, okay, and the commutation relations. So let's just check the commutation relations. So it is clear that these two operations give you different results in general. Namely, if I first create a boson and then I destroy that boson, it is not the same as if I first destroy the boson and I create the boson. So how come? You may think, well, they should be the same. Since their wave functions, are interchangeable, so how come if I first create the boson and then destroy the boson, it's not the same as first I destroy the boson and then create the boson? So let's check. They are indeed not the same. So let's just do this operation on the vacuum state. So suppose I do this, and I do this, and I will show that they are not the same. So the first operation is simple, because if I destroy the boson on the empty state, I got what? 0, right? But if I first create a boson out of the vacuum, I got something, right? Not 0, okay? So which is what? Which is 1 times b nu j and 1. Okay, because b plus 0 is 1. So this is 1. But I have one operation remains, okay, which is to destroy the single boson again. And this time I get another prefactor, which is b minus 1. You see, b minus 1 is 1. So this is 1 times the empty state. So here comes the magic. If I subtract one from another, I get something finite. b nu j, b nu j. Dagger is a commutator, which is defined as b nu j, b nu j dagger minus b nu j dagger, b nu j, which is 1. Okay, so this is the third commutation relation for bosons, which is highly non-trivial. So here comes the homework. The homework is that to generalize this derivation for arbitrary initial states. To prove this for arbitrary general initial state, where the nu j and nu I are non-zero. Okay, so you are able to show this non-zero commutation relation between b and b dagger for most general arbitrary many boson wave function where nu I is some finite value and nu j is some other finite value. So they are not empty states. So what I mean is that they are not empty state. But this relation still holds for arbitrary many boson wave functions. And there's a delta function. So if I is the same as j, you get 1. If not, it is 0. So now let's combine those commutation relations. So b dagger, b dagger, b, and b, j, b dagger, nu k, delta, nu j, and nu k. So we will use this commutation relations in the following derivations of a general coefficients b plus and b minus. And by the way, you could also show this trivial commutation relations for arbitrary, say, many boson wave function. So let's fix the constant b plus and b minus. And we defined the number operator as we defined before for fermions. For bosons, the same, so which is simply just b dagger b and nu, wearing a hat, b dagger nu, b nu. So this number operators allows us to extract the occupation number for boson, for many boson system, if the boson stay in the quantum state nu. So let's just first derive this commutation relations between this number operator and either the destruction operator or the creation operator. So first we could prove that this commutator between this number operator and nu and the destruction operator B nu is going to be minus B nu. Okay, the way that we prove this is to use this commutation relations above. So this is the fundamental relation for a boson system that is satisfies this commutation relation. And we'll do that in just a moment. And we could also prove that, n nu, if I commute with B dagger nu, I get B dagger nu. And remember this n nu operator acting on any occupation number states reports me the eigenvalue as the occupation multiplied by this eigenstate of the occupation number operator. Okay, so this is by definition. So then we will derive the B plus and B minus accordingly. So let me just tell you the results, and then we could derive just in the next couple minutes. And B nu dagger acting on n nu, square root of n nu plus 1, n nu plus 1. So which means that B plus is square root of n nu plus 1, and B minus square root of n nu. That's the final answers. But the question is how can you derive this? Okay, so let's just fill out the gaps, and let's take a short break. When we come back, we will first derive these commutation relations, and then use these commutation relations to derive this B plus and B minus. So let's just very quickly go through the algebra, and you could do that at home. So let's just prove this. And we plug in this definition of the occupation number operator. And in quantum mechanics, you must have learned that if there is a commutator between A, B, and C, where A, B, each of this A and B is the quantum mechanical operator, then you could use this mathematical manipulation of this commutator and use this identity, and you get this B dagger nu, B nu, B nu, plus B dagger nu, B nu, B nu. I simply just plug in this ABC commutator here, and this is A, and this is B, and this is C. Okay, very simple. And you check these two terms separately. So first, if there are two operators and they are the same operators, and you put them in the commutator, you tell me what is this. If this is A commutator, you tell me what this is. This is A minus A, which is what? O, right? O. O means 0. Right? Okay? So that's trivial. Okay? So there's nothing to talk about this. 0. And what about the second term? Well, this is the thing that we mentioned, but with the reverse order. So this is minus 1. Remember, B dagger is actually 1. And this commutator refers to that, first this is left times right minus right times left, right? Which is minus the other way around. So if this is 1 and this should be minus 1, everyone agrees? Guys, simply just switch order between these two terms, I should get minus 1. And this is minus 1. And checked. Sounds simple, easy. So now is your homework. Your homework is do the other remaining derivations, proof the other. So n nu commutatus B dagger nu gives you B dagger nu. So you follow the same way that you proved this first relation, and it's easy, a piece of cake for you to prove the second relation. Okay? So This is trivial homework. So see, there are many straightforward homeworks like this. So if you could, simply just follow this lecture notes, and you'll get full 10 points for this homework. And you'll get a flying color for this course. So you will be satisfied. Because this is not hard homework if you know this. And this is simply just a simple extension of this derivation that you already learned. So now let's do this non-trivial part. So suppose I evaluate this thing. This is B nu, N nu. And I just square this, which is N nu, B dagger nu, B nu, and N nu. Suppose this is the operation. If I use this destruction operator, B nu, to destroy this boson number on nu by 1, and I square this, which means that this is nothing but just a matrix element, right? So because this square is that this, suppose this is some Dirac state, and this is nothing but this in quantum mechanics, right? Okay, and therefore I could just rewrite this in terms of this matrix element. But we know what this is on the right-hand side. So this is nothing but N nu operator acting on this N nu and N nu on the left and right. So this is nothing but N nu. But what is this on the left-hand side? So this is nothing but B minus and N nu minus 1, and I square this. And but what is this? So this is nothing but B minus square. There's an N nu minus 1 on the left and N nu minus 1 to the right. And by normalization, this is nothing but B square, B minus square times 1, because this is simply just normalized to 1. Therefore, you get B minus is square root of N nu. If you compare this results on the left-hand side and the right-hand side. So B nu, B minus square is N nu, and therefore B minus is the square root of N nu. Sounds magic, but it's not magic. It's just quantum mechanics and Dirac notation, that's all. And also the definition of the occupation number operator and the creation and destruction operators for bosons. So now you know what I'm trying to do. Can you predict my next sentence? Yes, you can predict. Homework. Okay, so I proved half of the coefficients, which is B minus. Then it's your job to derive the remaining half, which is B plus. And derive B plus, which is square root of N nu plus 1. Okay, following the similar path that we derived the B minus, you are able to derive the B plus in a straightforward manner. So once you convince yourself that they are really those coefficients, then we could really continue to build up our boson system. So I guess that's enough for today. And next Monday, we will switch gear again to the fermionic system, but we will come back to boson later. Okay, so when we talk about, say, harmonic oscillator or phonons or magnons, we will come back to the bosonic operators later. But now you have a complete picture what we can do to count this boson number and fermion numbers. And you could read many chapters in our textbooks without trouble. So I'll see you next Monday.